In this video we discuss the classifications of singularities. We know that if f of z has a singularity, say z0, which is isolated singularity, that means there exists a neighborhood in which there is no other singularity for f of z, then it has a Lorentz series expansion, f of z equal to etc. b2 by z minus z0 whole square plus b1 by z minus z0 plus a0 plus a1 z minus z0 plus a2 z minus z0 whole square, etc. So in fact the coefficients AI's comes from the positive powers of z minus z0, and BI's come from the negative powers of z minus z0. So using this Lorentz series of f of z, we can classify the singularity z0. If z0 is a isolated singularity, then if all the BI's are 0, that means there is no negative powers in the Lorentz series expansion of f of z at z equal to z0. Then we can, if BI is equal to 0 for all I, then we have removable singularity. We can call this z0 is a removable singular point. Removable singular point. If this BI's are finite, BI's equal to 0 for all but finitely many. That means only finite number of BI's are non-zero, other BI's are 0. That is the meaning of this. Then we have z0 is classified as pole. Z0 is a pole, which is called pole of f of z. And if BI's are non-zero, for infinitely many, i's, then this z0, for that corresponding z0 is called essential singular point. Essential singular point. We already discussed what is the residue of f of z at z equal to z0. That we have discussed earlier, but we write the definition of residue as well. Residue of f of z at z equal to z0 is the coefficient of 1 by z minus z0. So this coefficient in the Lorentz series, so that is what we call b1. Okay, so that is the coefficient of 1 by z minus z0 in the Lorentz series expansion. In the Lorentz series expansion of f of z at z equal to z0. That means if you expand that function f of z in a annular region about z0, then there is b1. b1 is the coefficient of 1 by z minus z0. That b1 is called the residue of f of z at z equal to z0. So we have seen that this is used to evaluate integrals as well. So first of all, we try to find how to evaluate the residue of a function that is at a singularity z0. So first of all, we need to write the Lorentz series expansion of that. Okay, so next we have residue of f of z at poles. Next we discuss how to evaluate residue of a function at poles. We know that for a pole, we have seen that the definition of pole, if you write the Lorentz series expansion at z equal to z0, then if BI's are only finite BI's are non-zero. That means all BI's but finitely many are zeros. Okay, in that case we call z0 as a pole. So we can expect that for a pole z0, f of z has a Lorentz series expansion as bm divided by, there is a finite number m such that bm divided by z minus z naught raised to m plus bm plus 1, or b, this is a minus 1 fact, this is bm minus 1, that is the previous coefficient, that is the coefficient of z minus z naught rotation m minus 1, plus b m minus 2 divided by z minus z naught whole raised to m minus 2 plus etc etc, b2 divided by z minus z naught square, b1 divided by z minus z naught whole raised to 1 plus a naught plus a1 times z minus z naught plus a2 times z minus z naught whole square, etc. So this will be the Lorentz series expansion of f of z if z naught is a pole. Okay, this m is what we call the order of the pole. If bm is the largest suffix for which largest non-zero suffix for which Lorentz series, so in that case we can call this f of z as a pole of order m at z equal to z naught. The next theorem says that how to evaluate the residue, or how to evaluate this b1 from this f of z. So next we discuss a theorem which states the residue of this type of f of z, that means f of z with the pole at z equal to z naught has a special form that is in the next theorem. We can state that theorem. Okay, theorem says that suppose z naught is the isolated singularity, z naught is an isolated singularity. Obviously there exists Lorentz series expansion for that f of z at z equal to z naught singularity. Okay, then we can say that z naught is a pole of order m. In fact, the definition is this one. If f of z has a pole of order m, means f of z takes this form. Okay, or Lorentz series will be of this form. If this is the case, then we will prove that this is if and only if f of z can be expressed as phi of z divided by z minus z naught raised to m. Okay, so whenever this f of z has a pole of order m at z naught, then f of z can be expressed as this form, where this phi of z is analytic. So you can find a analytic function phi of z such that f of z equal to phi of z divided by z minus z naught. Okay, is analytic. And moreover, in this theorem, this is also stated that residue of f of z at z equal to z naught. How to evaluate this? In order to evaluate this, you can use the make use of this phi of z. So that will be phi m minus 1. You need to differentiate phi m minus 1 times at z naught, and we use m minus 1 factorial. Using these two factors, this fraction will be the residue of f of z at z equal to z naught. Okay, for m is equal to 0, m is equal to 1, 2, 3, etc. So if m is equal to 1, then this will be phi 0 of z naught, that is phi of z naught itself. So this is the formula. So this is how we evaluate the residue of f of z at z equal to z naught if z naught is a pole of order m. Okay, to prove this, we write since we need to prove two implications. First of all, we need to assume that f of z has pole of order m. Then we will prove that there exists phi. Okay, and the other way, we assume that f of z has the form phi of z divided by z minus z naught raised to m. Then we will prove that f has a pole of order m at z equal to z naught. Okay, so to prove this, we first assume that f of z has the form phi of z divided by z minus z naught raised to m. First of all, assume that f of z can be written in this form using an analytic function. Phi of z is analytic. Okay, whenever phi of z is analytic, then phi of z has the Taylor series expansion at z equal to z naught, because our assumption that phi is analytic function. So every analytic function there is a Taylor series expansion. So we can write the Taylor series expansion of phi of z at z equal to z naught. That is in this form: phi of z naught plus phi dash of z naught divided by 1 factorial z minus z naught plus phi double dash z naught divided by 2 factorial z minus z naught whole square plus etc. So this is the Taylor series expansion of phi of z. Then how to find f of z? Then f of z will be phi of z divided by z minus z naught raised to m. So we need to divide this phi of z using z minus z naught raised to m. So the first term will be phi of z naught divided by z minus z naught raised to m plus phi dash of z naught divided by 1 factorial. When you divide this term with z minus z naught raised to m, then in the denominator we will have z minus z naught raised to m minus 1 plus etc. In the second term, the third term, phi double dash z naught divided by 2 factorial times z minus z naught raised to m minus 2 plus etc. plus etc. Finally we have there is a term containing phi m of z naught divided by containing this coefficient m factorial times z minus z naught raised to m. When you divide this term with m z minus z naught raised to m, then you will have only constant term phi m z naught divided by m factorial. The very next term we will have phi m plus 1 z naught divided by m plus 1 factorial times z minus z naught plus etc. So if you observe this series, then this is the series of f of z at z equal to z naught in the annual region, but this contains only a finite number of negative powers of this z minus z naught. So from this series we can say that this f of z has pole of order m. Okay, because this is the z minus z naught raised to m is the largest negative power of this f of z in the Lorentz series expansion. So it contains only a finite number of negative powers of z minus z naught. Therefore f of z has a pole of order m. So it is obvious that this expression is valid in the annular region, because if phi is analytic, then this expression is valid for mode z minus z naught raised z naught is less than some radius r. Then if you consider these terms, then this will be valid in the annular region about z equal to z naught. So which shows that this f of z has a pole of order m. On the other hand, we need to prove that whenever z naught is a pole of order m, then on the other hand we assume that z naught is a pole of order m. Then f of z takes the form bm divided by z minus z naught raised to m plus bm minus 1 divided by z minus z naught raised to m minus 1 plus etc. b2 divided by z minus z naught raised to 2 plus b1 divided by z minus z naught plus a naught plus a1 z minus z naught plus a2 z minus z naught square plus etc. So whenever we assume f of z has a pole of order m at z equal to z naught, then f of z has a Lorentz series expansion about the annular region of z about z naught. Okay, so this is valid for valid in this region. Okay, so in order to prove the phi of z f of z has a the form phi of z divided by something, we need to find out phi of z first. So we write a function in order to write suppose z is not equal to z naught. Okay, z not equal to z naught, then what is z minus z naught raised to m times f of z? If whenever this z not equal to z naught, you can multiply both sides by z minus z naught, then z minus z naught raised to m. In fact, both sides multiplied by z minus z naught raised to m, then left side will be this one and right side will be bm plus bm minus 1 divided by bm minus 1 times z minus z naught plus bm minus 2 times z minus z naught square plus etc. So this will be this product z minus z naught raised to m times f of z. Now we know that this function is defined z not equal to z naught. Okay, that means if you consider the annular region, okay, if we consider the annular region or puncture disk, so this is the our annular region. This is our annular region. So in this region we have the series expansion, or we can consider this this is convergent, right hand side is converges to the left hand side for every z belongs to this. You can shrink this inner disk as you as much as we want. Okay, that means you can shrink this disk very close to the point z. Now you write what is the limit z tends to z naught, z minus z naught raised to m f of z. You know that this is nothing but bm. When you take the limit z tends to z naught to this function, we can say that this is bm. Okay, so which shows that this function is continuous, or this, if you consider this function is continuous if we define the value of this function at z equal to z naught as bm. Okay, so this is the motivation to define a new function phi of z, which is equal to z minus z naught raised to m times f of z. So this happens if z not equal to z naught. At the point z naught, at z equal to z naught, we define this is equal to bm. Then you can easily prove that this phi of z is analytic. We know that this if we define in this manner, then you can write this is our phi of z naught. So whenever limit z tends to z naught, this will be phi of z, that is equal to phi of z naught. Then if you define phi of z in this manner, you can easily get this function is continuous. Similarly, you can get the power series expansion or Taylor series expansion for this phi of z at z equal to z naught. Then you can say that this phi is analytic as well. Now what is the relation between, we already discussed that this y of z, z minus z naught raised to m, phi of z equal to phi of z equal to z minus z naught raised to m times f of z. Obviously, whenever f of z not equal to z naught, you can write f of z equal to phi of z divided by z minus z naught raised to m. Okay, so we have f of z takes this form, f of z equal to phi of z divided by z minus z naught whole raised to m. So this proves the other part as well. So obviously this phi of z is analytic at z equal to z naught. So this proves for any function with whole of order m, then that function can be expressed as an analytic function divided by z minus z naught raised to m. So this proves the theorem. So using this this fact, we will find the residue of this f of z. How to find the residue of f of z? Residue of f of z is nothing but when you consider the Taylor Lorentz series expansion of f of z and pick the coefficient b1. This b1 is to be defined as the residue of f of z at z equal to z naught. So how will you find b1 using this f of z? Okay, so in order to get f of this b1, we first multiply f of z with z minus z naught raised to m, then you will get this one. Clear? When you differentiate this expression, or this is in fact phi of z, so you differentiate this expression the m minus 1 times, the first time if you differentiate this first time, then this bm will be 0, or this term will be 0. The rest of the term will be bm minus 1 plus 2 times bm minus 2 z minus z naught. Okay, so if you differentiate this expression, I call it as 1. If you differentiate this expression, differentiate 1 m minus 1 times, you will get this will be dm minus 1 by dz m minus 1 z minus z naught raised to m f of z. That will be the left hand side. The right hand side will be the first in the first differentiation, this bm will be 0. The second differentiation, this term will be 0. And if you perform this m minus 1 times, then that will be m minus 1 into m minus 2 into etc. into 1 plus this will be m minus 2 into m minus 1 into etc. 2 times z minus z naught plus etc. So that means the first derivative we have this term will be a constant. The second derivative, this term will be a constant, and if we differentiate this m minus 1 times, then the m minus 1 power, the term will be the mth term will be the constant, so that is this term. So now from this you can take the limit of LHS and RHS as z tends to z naught. So we take limit z tends to z naught dm minus 1 by dz m minus 1 z minus z naught raised to m f of z equal to, this will be m minus 1 factorial. Okay, this will give, because when you take the limit z tends to z naught, these terms will be 0, so the remaining terms will be this one. Okay, so in fact, what is this one? Okay, this is nothing but the m minus 1 the derivative of phi of z. Okay, so this can be replaced as limit z tends to here we have b minus 1 as well, right? Sorry, b1 is there, because if you differentiate this first time, then you can cancel this and there will remain this b minus 1, and if you differentiate the second time, then this term will be cancelled and bm minus 2 is there, 2 times bm minus 2 is there, and similarly you can get this times b1 will be there, so this is b1. So from this you can write this is limit z tends to z naught. This is in fact phi m minus 1, the m minus 1 the derivative of this this function phi of z equal to m minus 1 times factorial times b1. And since we know that phi is analytic, then this m minus 1 the derivative of phi is also analytic. So if you take the limit z tends to z naught, phi m minus 1 z is will give the phi m minus 1 of z naught. Okay, so that will be m minus 1 factorial times b1. So what is b1 here? b1 is equal to phi m minus 1 z naught divided by m minus 1 factorial. So b1 is nothing but the coefficient of 1 by z minus z naught in the Lorentz series expansion of f. So that can be termed as residue of f of z at z equal to z naught. So that can be obtained as phi m minus 1 z naught divided by m minus 1 factorial. So if f of z has a pole of order m at z equal to z naught, then you can make use of that phi of z to evaluate the residue of f of z at z equal to z naught. So this completes that theorem. To illustrate this theorem, we discuss an example. Consider f of z equal to z plus 1 divided by z square plus 9. We know that since this is a rational function, so that is the quotient of two polynomials, so singularities of f of z can be obtained by equating z, the denominator of this rational function equal to with 0. Okay, so that will z equal to plus 3i and z equal to minus 3i. So these are two singularities of this function. So we write f of z is equal to z plus 1 divided by z plus 3i z minus 3i. Now we know that this is of the form, first of all we need to evaluate the residue of this function at z equal to z0. Z0 is 3i first. So we write residue of f of z. We use that theorem to evaluate the residue of this function at z equal to z0. So first of all we can evaluate residue of f of z at 3i. Okay, so in order to evaluate this residue, we express that f of z as phi of z by z minus the power of z minus 3i. So first we write f of z is equal to z plus 1 divided by z minus 3i, sorry, z plus 3i divided by z minus 3i. When you write this f of z in this fashion, you can say that this can be taken as phi of z, which is analytic at 3i, and this is z minus 3i raised to 1. So from this you can write, since the power of the denominator is 1, then we can write f of z has a pole of order 1. Pole of order 1. Pole of order 1 is called symbol pole. Symbol pole. So pole of order 1 at z equal to 3i. Now how you will evaluate residue at z equal to 3i of this function f of z. So using the previous theorem, this is phi of z, then that can be, since this phi is analytic, then and this z is equal to 3i is a pole of order 1, then we need to evaluate the derivative 1 minus 1, the derivative of phi of z at z equal to 3i divided by this 1 minus 1 factorial. In fact, m is equal to, in the previous theorem we can replace m by 1. So we have phi m minus 1, that is m minus 1 the derivative of phi at 3i, and m minus 1 factorial. Here the denominator will be 0 factorial, that is equal to 1, and the numerator will be 0th derivative of phi, that is phi itself, phi of 3i. What is phi? Phi of 3i is this one, that is 3i plus 1 divided by this is 3i plus 3i, that is 6i. So this is the residue of f of z at z equal to 3i. So this is obtained by replacing this z and z by 3i. Okay, so that will be 3i plus 1 divided by 6i. On simplifying you will get 6i, this is 6i on 6 factorial by 6i. So by rationalizing you will get this is equal to 3 minus I divided by 6. By multiplying numerator and denominator by I, you will get this is 3 minus I divided by 6. In the similar fashion, you can evaluate the residue of the same function, residue of f of z at z equal to minus 3i. Okay, so in that case we rewrite this f of z as z plus 1 times, divided by z minus 3i divided by z plus 3i. If you write f of z in this fashion, you can take this as phi of z, because this function is analytic at minus 3i. Okay, z plus 1 divided by z minus 3i is analytic at z equal to minus 3i. That means if you put z equal to minus 3i in this numerator, then that will be a non-zero quantity, that is a finite quantity, therefore that function will be, numerator will be analytic. In fact, this is the denominator has power 1, and again this f of z has a pole of order 1 at z equal to minus 3i as well. Now you evaluate the same, evaluate the residue using the same result, phi raised to n1 minus 1 times of minus 3i divided by 1 minus 1 factorial. If this is the case, we need to, in this case, we can consider this is the case 2, the residue at z equal to minus 3i, and this is the case 1, that is residue at 3i. So in the case 2, phi of z is this, we replace z by minus 3i, So that will be minus 3i plus 1 divided by minus 3i minus 3i, that is minus 6i. Okay, so this will give the residue of f of z at z equal to minus 3. By rationalizing, you will get this is equal to 3 plus I divided by 6. So this is the way we used the previous theorem to evaluate residues of a function f of z. Okay, if f of z has a pole of order m at z equal to z naught. Okay, so there are a couple of examples are discussed after this, so please go through it, and if you have any doubt, please let me know.